Alright, so today we want to explore our sine and cosine curves. We looked at these briefly earlier, very briefly.
Yeah.
But I want to look a little more closely at what periodic functions are, and then look specifically at sine and cosine and observe a few things about them. And also tie some things from the graph back to some things we've already learned, and hopefully it'll help make those things make sense even more, okay? So we've got this periodic function. If you look closely at the graph that I've shown you here, you might call this, what does that kind of look like?
Teeth.
Teeth?
Really weird looking teeth.
Volcano.
I was actually about to say that. It
Volcano?
looks like ogre teeth.
Ogre
Or-
teeth?
A bunch of capes lined up.
Yeah, it looks
Huh.
like some
Pictures of ants.
Or
A
like,
bunch of capes?
or
like-
you know Roman in Guardians of the
Antlers.
Galaxy? It looks
Yeah.
like the outline of his head.
Huh.
Each individual one.
We're- Or maybe Batman. That's what people usually say.
Batman.
Batman?
Yeah, if you cut it like this, you got the ears.
I don't like that.
Batman. Alright. So here's our Batman function. You know,
Oh, I see.
you got the eyes and
Oh, I see.
grr, you know.
You'd be like,
So. Alright, so there's our Batman function. But you notice here, all of you recognized whatever you thought it looked like, okay? All of you recognized here that we had something that was repeating, right?
Okay there.
So this repeating pattern is what makes this function what we call a periodic function, okay? If you say something happens periodically, you typically are referring to something that happens every once in a while and usually on a consistent basis, all right? Here we have a little bit more specific definition because if we have a periodic function, we have this portion of the graph that repeats not just every so often, but exactly a certain amount of time, or after a certain amount of time. Okay? So what I've highlighted here is one period of this periodic function. Okay, we would call it one period of the function. Alright, so you'll notice here we have a consistent distance from start to finish as this thing repeats. Okay? This distance here, in this case, happens to be how much? Can you tell?
2.
No?
No, 3, 4.
4, okay? So this one repeats every 4 units, okay?
Oh, the bottom, okay.
So from start to finish is 4 units. That distance that we see right there is what's known as the period, okay? And we will typically use a capital P to represent that period. Okay? Is everyone with me?
Yeah.
All right. Now, another feature that periodic functions have, all periodic functions have this period, this consistent distance between repetitions, okay? But we also have what's known as the amplitude. So if we look at the highest point, we'd call that the max, and it's going to be consistent for every iteration of the period here. Let's say that that goes up 3 units, okay? So our maximum is 3. If we look here at this down here, the minimum, if we count down here 1, 2, 3, the minimum would equal -3. So what's the distance here between the max and the min?
6.
It's 6.
Divided by 3 is 2.
So alright, so the altitude is gonna be that distance, 6, divided by 2. Okay? So our amplitude here is 3. Make sure you're thinking in terms of distance, not just the coordinates.
Are they always gonna be like equidistant from the midpoint? It's to say, like, the middle is 0, but one is -3 and the other one's gonna be 3. Is it always gonna be like that?
That's an excellent question. What we could have here, we actually could have a situation where this thing was translated up. It's not stretched or shrunken at all. It's just shifted up. So let's say we shifted it up 3 spaces, and now the it looks like this. Rough sketch here. Okay. Almost got it. Looks more like Owl Man right now, but we'll take it. Okay.
That looks like an owl.
Did I do anything to the amplitude?
No.
No.
Batman put on a little bit of weight.
So it's like, yeah. This is middle-aged Batman or geriatric Batman or something. All right. We've got now it's going to go from 0 up to 6. What's the distance between the max and the min?
6.
6. So the amplitude is still 3. Okay? So, even if it's shifted around, we may not, or because we can shift it around, there may not be an equal amount on the bottom and on the top. Okay? So that you always do want to look at the actual coordinates of the bottom and the top and find that distance. Alright, so that's an excellent question though. Now, let's say that this function is f of x. Okay? What would happen if I did 5 times f of x? What would happen to my amplitude and period?
It would all increase by 5. Like it would stretch by 5.
Okay, so what would my amplitude be now?
Your amplitude would be 15.
Very good. It would be 3 times 5. It would be 15. What would my period be?
20.
Okay, why?
4 times 5 is 20. But I'm probably gonna be like, it's wrong. No, because it doesn't only go up.
Not.
Okay, what kind of a transformation is this?
Horizontal. Or it's
Vertical.
outside, so it's vertical.
It's a vertical stretch. Does a vertical stretch do anything to the horizontal?
No,
so
No.
they stay the same.
So the period would stay the same here. Okay? The period would stay the same. Now, if I had f of 5x,
Oh,
that would be a little bit different, right?
the amplitude stays the same and period is 20.
Very good. Here, the amplitude would stay the same. What would the period be?
20.
All over.
It's horizontal, so there's an inverse relationship.
Oh, 4/5.
It's whatever B.
5 oh wait, 4.
4/5.
4/5.
Yeah, it would be 4 over 5. It would be 4 divided by 5. The original period was 4. You would divide it by that 5. Okay? So, the period would now be 4/5 of a unit.
So it shrinks.
So it would actually shrink it horizontal. It would be like something like this,
Is about to happen.
ending at 4/5. Okay, it would be shrunk really, really small. Okay?
It works better.
Hours and minutes or whatever.
Now, let's explore our sine function. Okay? The sine and cosine functions are.
Where's the green?
Glad you're paying attention. Okay.
Wait, where'd it go?
Hours.
Alright, so let's explore our sine function. And guys, let's practice our unit circle as we do it, okay? So everyone, join us here mentally, and let's figure these things out, okay? We're gonna graph y equals sine of x. So notice on my x-axis I've listed a whole bunch of angles, okay? Let's start with 0. What's the sine of 0?
Square root of 2 over 2.
I think it's undefined.
Wait, of 0?
There's none.
0.
Oh, 0.
It's undefined or there's none.
Oh,
No.
it's 1, 0. 1 comma 0, so it's 0.
0, yeah. That point at 0 degrees is the point 1, 0. Remember your y coordinate is the sine, so the sine of 0 is 0. Okay? How about pi over 4?
Square root of 2 over 2.
Oh, neat.
There we go, root 2 over 2, which is about 0.707. Okay? So we'll put that there. How about sine of pi over 2?
1.
1. You guys with me?
No.
Yeah.
It's all from our unit circle, the y coordinates on our unit circle. Okay? So at 3 pi over 4, where are we at?
Wait,
What's sine?
Square root of 2 over 2.
Square root of 2 over 2. By the way, we knew it would be because it's the same reference angle, right, as pi over 4?
Yeah.
So we know that they're all either positive root 2 over 2 or negative root 2 over 2 when it's a pi over 4. Okay? What's the sine of pi?
0.
0. How about the sine of 5 pi over 4?
Negative square root of 2 over 2.
Okay? Come on, everybody.
He's not giving
He's
any.
just fast.
Yeah, I'll just stop. Oh, you know, I'm ready for the unit circle.
All right.
It's too good.
How about sine of 3 pi over 2? Think about, see it on your unit circle. Come on, we're going around the unit circle.
0, negative 1.
Negative 1.
0,
Negative 1.
Come on.
It's the point 0, negative 1. So we're down here at negative 1. Okay? How about 7 pi over 4?
Root 2 over 2.
Yay.
Negative
Oh,
root
yeah.
2 over 2.
7, 7, 7.
And then 2 pi.
0.
We're back up to
I
0.
don't care for negatives.
Alright, so look. Here is
You're Batman?
our sine curve, not Batman.
Dang it.
No, 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 no,
That's a
no,
little
no,
flat
no,
on the
no,
bottom,
no,
but that's
no,
okay.
no.
Okay? So there is our sine curve. And we could keep going, right? We have negative angles. We could keep going past 2 pi and do another lap around the circle, but we won't for right now. Okay? So think with me here. If I have this point at pi over 2 and I'm up here at 1, what is, well, let's answer the questions down here and then I'll come back to that question because we need the period. Alright, what's our domain for the angle? What is x allowed to be?
Is that what asking the cosine?
Between negative 1 and 1.
No, that's not
That's x.
domain, that's
Oh.
Greater than all real numbers.
all real numbers. You can have an angle that's negative, positive, and everything in between, okay?
How come there's arrows at the end of it? Like, isn't it, since it's a circle, it wouldn't have go on to infinity, I guess?
Well, remember our angles in standard position. You can do another lap around the
Oh,
circle
right, right.
and another lap around the
Yeah.
circle, and you can keep going either direction forever. Okay? So this is all real numbers. Alright? Our range, what was our range, Samantha?
Negative
N-
one. Oh, go ahead.
between negative 1 and
Everyone, we're calling grades
Okay.
from now on.
Negative 1 and 1. Alright? Notice I use the brackets because it does equal negative 1 and positive 1. Okay? Now, what's our amplitude for
One.
sine?
1.
1.
1. We're going from negative 1 to positive 1. That's a distance of 2. Divided by 2 is 1. And then how often is this thing repeating?
Once
Pi.
every pi.
What?
Pi.
Once every pi.
Let's look at it.
Oh,
Here's
it's
pi. Does it repeat the same thing?
That's filming.
Oh, once every 2 pi?
Once every 2 pi. Yeah, it has to go through the full circle, 2 pi, before it starts to repeat. Okay? So our period here would be 2 pi. Now, that's cool because, watch this. If I know that the sine of pi over 2 is 1, If I go over another 2 pi, here's 1 pi, 2 pi over here would take me to 5 pi over 2.
Same point.
Guess what the sine of 5 pi over 2 equals?
One.
1. And if I went over to 9 pi over 2, guess what sine equals? 1. And sine of 13 pi over 2 equals 1. That's what makes this thing periodic. Okay? The sine of pi over 4 is root 2 over 2. If I go over 2 pi until I have 9 pi over 4, guess what the sine is?
Root 2 over 2.
It's root 2 over 2, because this is periodic. Okay? So, that's something that we can recognize there. Even though we only graphed one period of this, it keeps going forever. And yet those values are going to repeat every 2 pi. Okay? Now, I want to observe something down here. Here we only put 5 points. And by the way, anytime I ask you to sketch sine or cosine, and we'll go over this again later, but I want 5 points. Notice here on sine, we have a starting, a middle, and an end point that are all on this middle line. And then between the first two is the max, and between the third and fifth is the min. Okay? So I'm going to be looking for the midline points, the max, and the min. Those 5 points. But let's observe something else here. From here to here is what on my unit circle?
First quadrant.
The first quadrant. Okay, that's my first quadrant. And then from pi over 2 to pi is what?
Second.
Second quadrant. Alright, we're catching on. From there to there is our third quadrant.
No, how do I know?
And then from 3 pi over 2 over to 2 pi is the fourth quadrant. Okay? Now,
Same thing.
what did we learn yesterday, or not yesterday, but what did we learn before about sine in the different quadrants?
It's negative
it's
in
the
4
y?
and then positive
Oh,
in
it's
1
cat.
and 2.
It's negative in 3 and 4, and it's positive in 1 and 2. Well, look at our graph here, guys. Here's quadrant 1 and quadrant 2. Where is our graph of sine?
Negative. No?
In 1 and 2?
Oh, I thought you were
Positive.
talking about the other.
Sorry, that's alright. It's positive, it's above the x-axis, right?
So that means that sine is always negative in 3 and 4.
And look, yeah, here in 3 and 4, we're below the x-axis.
You failed me. Negative.
So here we're negative. Whoop.
Yay,
Now it's
30
That's
seconds.
alright, at least we're awake here.
I can't slow time down for you.
You have to.
Alright, so, guys, this confirms what we saw about all students take calculus, alright? Sine is only going to be positive in that first and second quadrant, and we can see that right here in the graph, okay?
Why is tangent not positive in the second? It might be negative.
I'm gonna hate you.
Wait. Why is it not negative if cosine is negative in the second?
I was looking at that card because it's 26 now.
Because if tangent is sine over cosine, then if cosine is negative, then tangent should be negative.
It is.
Oh, it is?
In the second quadrant.
Oh.
In the third quadrant, though, both sine and cosine are negative, so that makes tangent a positive, okay? Now, let's cosine in a similar way, okay? And this one will go a little faster now that we've got the hang of it, hopefully. Alright, what's cosine of 0?
Zero.
No!
No!
You guys
One.
are so bad.
It's 1.
Cosine is the x-coordinate, right?
Oh,
no.
So what's cosine of 0? 1.
You made it sound like it would be the
Someone
same
just said
thing.
No.
So
Alright,
easy.
what's What's cosine of pi over 4?
Square root of 2 over 2.
Square root of 2 over 2. Alright, so here's root 2 over 2.
0.
Cosine of pi over 4 is that. What's cosine of pi over 2?
0.
0. Cosine of 3 pi over 4?
Root 2 over 2. Negative root 2 over 2.
Negative root 2 over 2. There we go. Negative root 2 over 2. And how about cosine of pi?
Negative 1.
Negative 1. Cosine of 5 pi over 4?
Negative root 2 over 2.
Cosine of 3 pi over 2?
0.
Cosine of pi over 4, 7 pi over 4?
Root 2 over 2.
And cosine of 2 pi?
1.
1. And you'll notice here,
Wait, what?
we have a very similar shape. In fact, it's exactly the same shape.
Stops it.
It's simply shifted over. Okay?
Yeah.
This is going to keep going like this. This is going to keep going like this if we were to continue.
No Batman.
Alright?
Batman.
It's just like the sine, but it's shifted over. Okay? So, what's the domain?
All real numbers.
That's right. The domain is all real numbers. What's our range?
1, negative 1.
Negative 1 to 1. What's our amplitude?
1.
1. The distance between the lowest point at negative 1 and the highest point at positive 1 is 2. So 2 over 2 is 1. What's our period?
2 pi.
2 pi. Okay? 2 pi. So all of these are exactly the same as sine. Okay? And again, that goes back to because sine and cosine are just the same thing but shifted over pi over 2. Okay? So, now let's make the same connection we did with sine here.
Cosine is
Okay.
positive and all that good stuff.
Where is cosine
1
positive?
and 4.
In the first quadrant and in the fourth quadrant. You can see that right here. Cosine is positive here in the first quadrant and in the fourth quadrant. Okay? Ooh. Cosine is negative in the second and the third quadrants. And that coincides with what we've seen, where all trig functions are positive in the first, only the sine is positive in the second, only the tangent is positive in the third, and the cosine is the only one positive in the fourth. Okay? One really common mistake, guys, is that people mix up the sine and cosine graphs. Which one starts up at 1, which one starts at 0. If you keep all students take calculus in mind, it's really easy to keep them straight. Okay? Because the sine's got to be above the x-axis in the first 2 quarters. Okay? Cosine has to be above the x-axis at the beginning and at the end. Alright? Make sense? Okay. Now, we're going through all of this because we need to be able to use these. We're going to use these starting tomorrow to transform the graphs.
Oh no.
And actually to sketch these in a transformed way, okay? As we looked at with the Batman function, when we have 5 times f of x, it's stretching our amplitude. Well, that's not just with that function, that's with even the sine. The sine typically has an amplitude of 1, but if we did 5 times the sine, the amplitude would be 5. Okay? And same thing with the horizontal, stretching and shrinking, and also the translating. It all works the same because sine of x and cosine of x are just 2 new parent functions. That's all they are. They're two new parent functions. All the transformations and even reflections work the same way. Okay? Yes?
What's that?
What, this?
Mhm.
Well, this right here, if you wanted like the first period, what normally would go from 0 to 2 pi will end up in this range. We're gonna explore that a little bit more closely, but you'll notice the period
Yeah, that's
of the transformed one will always be 2 pi divided by b.
because your thing always ends at two, like a full circle, it's a full unit circle.
Yeah, it's always a full circle, but it's gonna be shrunken by whatever b is. Okay, so 2 pi divided by b. You'll also notice here, this is actually our horizontal shift. Instead of starting at 0, we're gonna start at c divided by b. And again, we'll look at that tomorrow. The reason why we wanna look at all of this and learn how to work with these things, guys, is because we're gonna use this to create models. Anything in life that goes in a current or a consistent pattern like this, going up and down and up and down, can be modeled with a sine or a cosine curve. It's just a matter of adjusting the period, and the amplitude and translating it over to where you need to start, okay? So, whether it's the phases of the moon, or whether it's the depth of the tide at a certain dock, or whether it's how much daylight we have on a particular day of the year, or even the temperature in the room as the thermostat turns on and turns off and turns on and turns off throughout the day, we could model all of those with periodic functions. Okay? So, kind of a cool thing that we can use.